Welcome back to General Calculus, and today we are going to talk about piecewise functions.
Piecewise functions are functions that are defined by different formulas in different parts of their domains. Perhaps this definition will make more sense by way of example. So let's take a look at this piecewise function. F of x is defined to be x plus 1 whenever x is greater than 1, and 2 whenever x is less than or equal to 1. So in this example, the domain of the function is the set of real numbers, but we split that into two parts. The part where x is greater than 1, and the other part where x is less than or equal to 1. And in each of those parts, the function is defined by a different formula. So let's first get an idea of how this function works by plugging in some input values and seeing what pops out. Okay, so first, let's try x is equal to 0. Well, since piecewise functions have different formulas for different parts of the domain, we must be careful. Okay, so let's think about it. 0 is indeed less than or equal to 1. So it falls under the x less than or equal to 1 category, and the formula tells us that we have 2. So f of 0 is 2. Great. Now let's try x is equal to 1. This is actually kind of tricky because it's right at the border, right? But we know that 1 is less than or equal to 1 because that's where the equal sign is. So we are still going with the x less than or equal to 1 part of the domain, and we get 2 again. So f of 1 is 2. Okay, finally, let's try x is equal to 2. This time, we know that 2 is greater than 1, so we are going with the x greater than 1 part of the domain, and we're using the formula that f of x is x plus 1. So, plugging in x is equal to 2, we get 2 plus 1, which is equal to 3. So f of 2 is 3. Awesome. In a similar manner, we can plug in a bunch of different values of x and create a table of inputs and outputs, just like we did in our previous video. Once you do that, we get something like this. So this table tells us that f of 4 is 5, for example. And now that we have this nice looking table, we can also plot a graph of the function. Plotting x on the horizontal axis and y on the vertical axis as usual, we do the same exercise we did in our previous video and plot each point. So the first point is, for example, negative 4, 2, which is right there. The second point is negative 3, 2, which is right there, etc. And we get all of these different points. And finally, we connect all of these dots to get this beautiful graph. There you have it, a piecewise function that looks like the constant function f of x is 2, where x is less than or equal to 1, and the function f of x is x plus 1, where x is greater than 1.
A really common example of a piecewise function is one that you've likely already come to know and love throughout your previous math classes. This is the absolute value function f of x equals the absolute value of x, or the function that always returns the positive version of whatever is inside the two bars. This is a piecewise function because it can be thought of as following two separate rules depending on the value of x. Suppose x starts out positive, or 0. Then taking the absolute value has no effect on it, meaning that f of x equals x when x is greater than or equal to 0. However, when x starts out negative, we have to change the sign of it, which has the same effect as multiplying x by negative 1. So f of x equals negative x when x is less than 0. Combine these two rules and we write f of x equals the absolute value of x as the piecewise function f of x equals x when x is greater than or equal to 0, and negative x when x is less than 0. Let's test this to make sure it matches. Try x equal to 2. F of 2 equals the absolute value of 2, which is just 2, in the normal way of thinking about it. Or, we can say that since 2 is greater than 0, we will follow the first rule in the piecewise version, f of x equals x. So we get f of 2 is equal to 2. But what if we start with x equal negative 1? Well, normally, we would take f of negative 1, which is equal to the absolute value of negative 1, which is just 1. Or, if we wanted to use the piecewise function, since negative 1 is less than 0, we're going to use the second of the two rules for f, or f of x is equal to negative x. So we get f of negative 1 is equal to negative 1, which is just equal to 1. This agrees with the other way of using the absolute value function, as expected.
All right, for our third and final example of a piecewise function, let's look at something a little more involved. So here is the challenge example. F of x is defined to be 2x minus 3 whenever x is greater than 2, and it's defined to be negative x plus 1 whenever x is greater than or equal to negative 1, but less than or equal to 2. And finally, it's defined to be x squared whenever x is less than negative 1. For this example, let me first give you the graph of the function, which looks like this. A couple of new things are introduced here. First of all, you will notice that there are jumps when the piecewise function switches from one formula to another. You will also notice that whenever there is a jump, there is an open circle on one end and a closed circle on the other. This notation is related to where the equal signs are placed when we split up the domain of the function. In this case, you will notice that the first part is x less than negative 1. No equal sign attached there. So we draw an open circle there to indicate that that point is not included. On the other hand, the second part, where it says x is greater than or equal to negative 1 and less than or equal to 2, well, that does include an equal sign at negative 1. So we draw a closed circle there to indicate that that point is included with the second part of the domain. Similarly, at 2, the second part of the domain carries the equal sign. So we have a closed circle there and an open circle where the third part of the domain begins. Keeping this in mind, you can now read complicated piecewise functions, including jumps. For instance, f of negative 2 is 4, f of 0 is 1, and f of 3 is 3. Okay, fine. That was pretty easy. But now that you know the open circle, closed circle notation, you can figure out what f of negative 1 is by looking at the location of the closed circle and not the open circle. So we have f of negative 1 as 2. Similarly, at the other transition, f of 2 goes with the closed circle, so f of 2 is negative 1. Awesome. Now you know how to combine different functions piece by piece, just like Legos.
So in this video, we introduced you to the world of piecewise functions. We looked at 3 examples of piecewise functions and how to work with them. Specifically, the second example we talked about, the absolute value function, is a particularly important one, and we will most definitely encounter absolute value functions again at a later point in the video series. So with that, see you in our next video where we will continue to talk about functions and models.